Volt-Amperes, or VAR, is indeed calculated by multiplying the voltage in volts by the current in amps. It represents a measure of apparent power. Apparent power is the total power delivered to a load. This includes both real power and reactive power. VA is commonly used in alternating current or AC circuits. This is because in AC circuits, voltage and current are not always perfectly in phase with each other. Let's delve deeper into these concepts to provide a clearer understanding. Consider a simple direct current or DC circuit. In a DC circuit, the voltage and current are always in phase. This means that the voltage and current reach the maximum and minimum values at the same time. In this scenario, the power consumed by the load is simply the product of the voltage and the current expressed in watts. However, in AC circuits, the situation is more complex. Inductive loads, such as motors and transformers, and capacitive loads, such as capacitors, cause the current to either lag behind or lead the voltage. This phase difference between voltage and current affects the power calculations. Real power, measured in watts, represents the actual power consumed by the load and converted into useful work, such as heat or mechanical energy. Reactive power, measured in volt-amperes reactive, or VAR, represents the power that is stored and released by reactive components like inductors and capacitors. This power does not perform any useful work but circulates between the source and the load. The apparent power, or VAR, is the vector sum of the real power and the reactive power. It represents the total power that the source must supply to the load, regardless of the phase relationship between voltage and current. Think of it like this: if you have a purely resistive load, such as a heating element, the voltage and current are in phase, and all the power delivered is real power. In this case, the VA is equal to the watts. However, if you have a load with a significant inductive component, such as a motor, the current lags the voltage. This means that some of the power delivered is reactive power, and the VA will be greater than the watts. The ratio of real power in watts to apparent power in VA is called the power factor. The power factor is a number between 0 and 1 that indicates how effectively the electrical power is being used. A power factor of 1 means that all the power delivered is real power, while a power factor of less than 1 means that some of the power is reactive power. Utility companies often charge customers with low power factors because they have to supply more apparent power to deliver the same amount of real power. Therefore, it is important to improve the power factor of electrical systems to reduce energy costs and improve efficiency. Power factor correction can be achieved by adding capacitors to the system to compensate for the inductive loads. These capacitors supply reactive power, which reduces the amount of reactive power that the utility company has to supply. In the context of power-limited fire alarm circuits, the 100 volt and 100 VA limitation is in reference to Article 760 of the National Electrical Code, or NEC. These limitations are in place to ensure the safety of the system and to prevent overcurrents and fire hazards. The 100 volt limitation is the maximum voltage allowed in these circuits, while the 100 VA limitation is the maximum apparent power that the circuit can deliver. These limitations are based on the assumption that the circuit is power limited, which means that it is designed to prevent excessive current flow. Power-limited circuits typically use current-limiting devices, such as fuses or circuit breakers, to protect the circuit from overloads. In inherently limited power-limited fire alarm circuits, the power source itself is designed to limit the current and voltage to safe levels. This can be achieved by using a transformer with a limited output voltage and current, or by using a power supply with built-in current-limiting circuitry. These types of circuits are considered to be safer than non-power limited circuits because they are less likely to cause fires or electrical shocks. When working with low-voltage systems, it is important to understand the concepts of voltage, current, power, and apparent power. It is also important to be familiar with the relevant codes and standards, such as Article 760 of the NEC. By understanding these concepts and standards, you can ensure that you are working safely and effectively. To further illustrate the relationship between real power, reactive power, and apparent power, consider a right triangle. The base of the triangle represents the real power in watts. The height of the triangle represents the reactive power in VAR. The hypotenuse of the triangle represents the apparent power in VA. The angle between the base and the hypotenuse is the power factor angle. The cosine of this angle is the power factor. The power factor can also be calculated by dividing the real power by the apparent power. For example, if a load consumes 1000 watts of real power and has an apparent power of 1250 VA, the power factor would be 1000 divided by 1250, which equals 0.8. This means that the load is using 80% of the power delivered to it effectively, and 20% of the power is being used to create an electromagnetic field. Understanding the power factor is crucial for optimizing electrical systems and reducing energy waste. By improving the power factor, you can reduce the amount of current required to deliver the same amount of real power. This can lead to lower energy costs and improved system performance. There are several methods for improving power factor, including adding capacitors to the system, using synchronous motors, and installing active power factor correction devices. Capacitors are the most common method for power factor correction. They work by providing reactive power that cancels out the reactive power produced by inductive loads. Synchronous motors can also be used to improve power factor. These motors can be operated at a leading power factor, which means that they supply reactive power to the system. Active power factor correction devices are electronic devices that actively control the current waveform to improve the power factor. These devices are typically used in high-power applications where precise power factor control is required. In summary, VA or Volt-Amperes is a measure of apparent power that takes into account both real power and reactive power. It is an important concept in AC circuits where the voltage and current are not always in phase. Understanding VA and power factor is essential for designing and operating efficient and safe electrical systems. Always refer to the NEC and other relevant standards for specific requirements and guidelines. When analyzing AC circuits and electrical systems, several instruments and tools can aid in understanding and measuring various parameters. Multimeters are essential for measuring voltage, current, and resistance. They are versatile and can be used for both AC and DC measurements. Clamp meters are used to measure current without breaking the circuit. They clamp around a wire and measure the magnetic field produced by the current flowing through it. Power analyzers are sophisticated instruments that measure voltage, current, power factor, real power, reactive power, apparent power, and other parameters. They provide a comprehensive view of the electrical system's performance. Oscilloscopes are used to visualize voltage and current waveforms. They can help identify phase differences, harmonics, and other anomalies in the AC signal. Power quality meters are specialized instruments that monitor the quality of electrical power. They can detect voltage sags, swells, harmonics, and other disturbances that could affect equipment performance. These instruments and tools are invaluable for troubleshooting electrical problems, optimizing system performance, and ensuring safety. Remember to always use appropriate personal protective equipment, or PPE, when working with electrical systems. This includes safety glasses, gloves, and insulated tools. Never work on live circuits unless absolutely necessary, and always follow lockout-tagout procedures to de-energize the circuit before working on it. Understanding the principles of electricity and using the right tools and equipment are essential for working safely and effectively with electrical systems. The concepts we've discussed have broad applications across various fields. Firstly, in electrical engineering, understanding VA is crucial for designing and analyzing power systems, distribution networks, and electrical equipment. Electrical engineers use VA calculations to determine the appropriate size of transformers, generators, and other equipment to ensure that they can handle the load demand. Secondly, in electronics, VA is important for designing power supplies, amplifiers, and other electronic circuits. Electronic engineers use VA calculations to ensure that the components in the circuit are not overloaded and that the circuit operates efficiently. Thirdly, in building construction, VA is used to determine the electrical capacity of buildings and to design electrical systems that meet the needs of the occupants. Building designers use VA calculations to ensure that the building has enough electrical power to support lighting, heating, air conditioning, and other electrical equipment. Fourthly, in renewable energy, VA is important for designing and analyzing solar power systems, wind power systems, and other renewable energy systems. Renewable energy engineers use VA calculations to determine the size of the inverter, charge controller, and other equipment needed to convert the renewable energy into usable electrical power. Understanding VA is essential for anyone working with electrical systems, whether it is an electrical engineer, electronics technician, building designer, or renewable energy installer. By understanding the concepts of voltage, current, power, and apparent power, you can ensure that you are working safely and effectively, and that you are designing and operating efficient and reliable electrical systems. Also, always adhere to national and local electrical codes for safe installations and operations. Consider the example of a small office building. The building has lighting, computers, air conditioning, and other electrical equipment. To determine the electrical capacity of the building designer must calculate the total VA of all the electrical equipment. The designer would start by listing all the electrical equipment in the building and determining the VA of each piece of equipment. The VA of each piece of equipment can be found in the equipment's nameplate. For example, a computer might have a nameplate that says 120 volts 2 amps. This means that the computer has a VA of 120 volts times 2 amps, which equals 240 VA. Once the designer has determined the VA of all the electrical equipment, they would add up all the VA to get the total VA of the building. The total VA is then used to determine the size of the electrical service, the size of the transformer, and the size of the circuit breakers. If the total VA of the building is 10,000 VA, the designer would need to install an electrical service that can handle at least 10,000 VA. They would also need to install a transformer that can handle at least 10,000 VA. And they would need to install circuit breakers that can protect the electrical circuits from overloads. The NEC provides guidelines for determining the electrical capacity of buildings. The NEC provides tables that list the VA per square foot for different types of buildings. The NEC also provides tables that list the VA for common electrical equipment. Understanding these concepts and tables is essential for designing safe and efficient electrical systems. When dealing with nonlinear loads such as electronic devices with switching power supplies, the current waveform is often non-sinusoidal even when the voltage waveform is sinusoidal. This results in harmonic currents which contribute to the apparent power but not to the real power. The presence of harmonic currents increases the VA and can lead to overheating of transformers and other electrical equipment. To mitigate the effects of harmonic currents, harmonic filters can be installed. Harmonic filters are designed to reduce the amplitude of harmonic currents and improve the power quality. In summary, VA is a fundamental concept in electrical engineering and is essential for understanding the behavior of AC circuits and electrical systems. It is used to determine the total power delivered to a load, taking into account both real power and reactive power. Understanding VA is crucial for designing safe and efficient electrical systems and for optimizing the performance of electrical equipment. The NEC is a comprehensive set of standards that provides guidance for the safe installation and operation of electrical systems. It is important to be familiar with the NEC and to follow its requirements when working with electrical systems.